In order to find the equilibrium concentrations when we're given the initial concentrations in our chemical reaction and our equilibrium constant, there's a couple steps that we need to follow. First, we need to figure out if the reaction is going to proceed in the reverse or in the forward direction. In order to do that, we are going to find our Q value. Okay. Once we know which direction the reaction is going to proceed, we're then going to define the changes of our reactants and products in terms of X. We're going to use the coefficients from our balanced chemical equation as the coefficients for X in our ICE table. And the X change is positive for the products. If we're proceeding in the forward direction, we're going to be making products. If they're reactants, then X is going to be negative because we're going to be decreasing the amounts. So if they're reactants, we're going to have a negative X value. Then we can solve for X. We may need to take the square root of both sides or even use the quadratic equation in order to solve for X. We can also simplify and approximate answers if we have very large concentrations or very small equilibrium constants. Let's look at an example. If we have the reaction of iodine and chlorine producing 2ICl, we're told that the initial partial pressures for both reactants and the product are 0.1 atmospheres, and we want to find the equilibrium concentrations. We're going to set up an ICE table. An ICE table, remember, is initial change in equilibrium, and determine the direction that the reaction is going to proceed. So we're going to find our Q value. It's going to be the partial pressure of the products, because there's a coefficient of 2, it's squared, divided by the partial pressure of the reactants. So now we can substitute in our partial pressures. And we find that our Q value is 1. So 1 is smaller than 81.9. So our Q value is smaller than our Kp. So that means that our reaction is going to proceed in the forward direction. Now we want to represent the change in terms of X. So our reactants are going to decrease, so they will be negative, by a certain partial pressure, which is X. And because both of them react 1 to 1, they're both going to be minus X. The product has a coefficient of 2, and we're going to form product, which means it's going to be positive. That coefficient of 2 means that for every X partial pressure we decrease, we're going to form 2X of our product. So now we're going to add the columns together in order to determine what the concentrations will be at equilibrium. So we'll have 0.1 minus X for the iodine. We'll have 0.1 minus X for the chlorine, and we'll have 0.1 plus 2X for our ICl. Now we can substitute this into our equilibrium constant expression. So our Kp is 81.9. We're going to put in our equilibrium concentrations. For the P, or the partial pressure of ICl, it's 0.1 plus 2x, and that whole thing is squared. For the iodine, it is 0.1 minus x, and for the chlorine, it is 0.1 minus x. So this is our new expression. We can simplify it just a little bit because we have 0.1 minus x and 0.1 minus x. That means that the denominator can be squared. And now we're going to solve for x. So we had 81.9 equals 0.1 plus 2x squared over 0.1 minus x squared. Now in order to solve for x, we can take the square root of both sides. This is going to take a little bit of simplification. So we get 81.9 square root is equal to 0.1 plus 2x divided by 0.1 minus x. Now, we're going to have to solve this, so we will need to move the denominator over to the left-hand side. And we start simplifying. So we're going to multiply through. Okay, we can move the x to the other side and move the 0.1 so that we're trying to group like terms. And now we can simplify. And solve for x. Oops. Okay, so that is our x value. So now that we know x, we can find our equilibrium concentration because we know that our change was minus x for both the reactants. We know for the product it was plus 2x. And so now we can add our initial concentrations to find out our equilibrium concentration. Oops, 4.6. And if we want to double check to make sure that we've done it properly, we can substitute it into the Kp value and put our pressure that we found into this value and see what we end up for the Kp. If we're close to our equilibrium constant, we know that we've properly solved our equation. And so we get a value of about 83. Our equilibrium constant was 81.9. So we're a little off, but within significant figures. And so this means that our answer, which each one of them have a little bit of rounding, so our answer is appropriate and correct. Here's a practice for you to try. See if you can determine the equilibrium concentrations for iodine and iodide. You will need to use the quadratic formula in order to solve. Because our initial concentration for the products is 0, Q is going to be 0, and our reaction is going to proceed in the forward direction. So we will set up an ICE table for our reaction. Remember, our reaction is I2 yields 2I. Our initial concentration, the change, and the equilibrium. So initial for our iodine was 1 mole placed in a 2-liter flask. So 1 divided by 2, our concentration is 0.5 molar. For the I, it is 0. The I2 is our reactants. It's going to decrease by X. And our products, because of the coefficient, it's going to increase by 2x. So because the coefficient is 2, we produce 2x. At equilibrium, we have 0.5 minus x and 2x for our product. So our equilibrium constant is I and squared because of the coefficient over I2. We can plug those values in. So our equilibrium constant was 3.76 times 10 to the negative 5th. We have 2x squared over 0.5 minus x. Now again, we're going to have to simplify this. So we're going to move the denominator over to the side with our equilibrium constant. And 2x squared, so 2 squared is 4, x squared. Now we're going to multiply through, and we get 1.88 times 10 to the negative 5th minus 3.76 times 10 to the negative 5th x equals 4x squared. If we rearrange this so that we get the form we can use for our quadratic equation, and we can plug this in to find x. So minus b, which would be the 3.76 times 10 to the negative 5th, plus or minus the square root of b squared minus 4ac. So a is 4, c is our constant, all divided by 2a. So what that's going to look like is x equals negative 3.76 times 10 to the negative 5th plus or minus square root 3.76 times 10 to the negative fifth squared minus 4 times 4. Oops, let me make that a little neater. Sorry. 4 times 4 times the negative 1.88 times 10 to the negative fifth all over 4a, which is 4. Okay, if we solve that, and there are quadratic equation solvers that you can use, we end up with x equals 0.00216. Remember, only one root will give you a reasonable answer because we're talking about concentrations. So only one of the roots will be reasonable. Okay. So now we can figure out what those changes are. So x is going to be 0.00216. So if we look at our ICE table again, so 0.5 is what we started with and 0. So we're going to subtract 0.00216 and add 2 times 0.00216. And so at equilibrium, so our reactants are favored in this case. We didn't change the reactants by very much. Okay. And now if we want to double check to make sure that we've done it properly, we can go substitute it into our Kc. To see if we get something close to our equilibrium constant. So this is just a way to check our work. And we get 3.75 times 10 to the negative fifth, which is good because we started with 3.76 times 10 to the negative fifth. So we know that we've solved it appropriately. And so our equilibrium concentrations for the I2 are going to be 0.498 molar and 0.00432 molar.